Okay, guys, welcome to today's lesson in statics. Today we're covering problem number 53 from chapter 3. So number 53 says, to loosen a valve, a force of magnitude 70 pounds is applied to the handle of the valve. Knowing that theta equals 25 degrees, moment of the x is negative 61 foot-pounds, moment about the z-axis is negative 43 foot-pounds. Determine phi and the distance d. So looking at this diagram, first we notice we have our force acting at point A, so we will need to write out our moment equation. We have a moment about the origin is equal to the position vector going from origin to point A cross the force acting at A. Now I've gone ahead and drawn out a few diagrams to show what the force acting at A, how it breaks down and decomposes into components. If we notice, looking at our position vector in the orange, on the diagram here now, if we notice at point A, we have two angles affecting the components of the force F. So breaking this down into 2D drawing, along the horizontal distance we have force in the y direction pointing down. It would be the sine of theta based off this diagram. So we have our forces, right our forces. We have our force in the x direction equal to F times some of these cosines and sines. We'll figure this out in a second. Next, we're going to go down to the y, though. The y we can figure out first, and then the z will go from there. So, in the y-axis, we look at how it breaks down in a 3D view, as well as this 2D drawing of here. We have Fy pointing down in the j-hat direction, the negative j-hat direction. It's pointing down times sine F sine of the angle theta. So actually we'll write these all as force vectors. We can include the sines with these components. So it would be negative F times the sine of theta in the j-hat direction. Okay, now going back, looking at the force X, looking at the diagram, it has the total force has a horizontal component, which would be F horizontal, which is equal to F times the cosine of angle theta. So X would be F times cosine of angle theta. That would get it into the XZ plane, and then look at it as this angle phi. Breaking this down into our components on the horizontal, look, this drawing is equivalent to this one where it points out of the point A. Cosine of phi would give us the x component. So it would be this horizontal force, F cosine theta, times now cosine of angle phi. Looking at in the I-hat direction. Looking at the z force, it's also in this horizontal plane, but it's multiplied by the sine of angle phi to get this component going in the positive z direction. So it would be F cosine of theta through the horizontal force in the xz plane, then multiplied by the sine of angle phi. And this is in the k-hat direction. So we have our three forces, our components of our force. Now we simply need this position vector going from O to A. So the position vector R is shown in orange. And I can remove it and then draw it again, going from the origin to point A would be R from O to A. It appears in the diagram we're going 4 inches to the left, which would be in the negative x direction. So it would be minus 4 I hat. We appear to be going up 11 inches in the positive y direction, so it would be plus 11 j hat. And then we appear to be going a distance d in the negative z direction, so it would be minus d for that dimension in the k-hat direction. Now we have everything we need. We can plug our values into our moment equation. This moment equation will become the cross product of the position vector O to A times the force applied at A. So to write this out, we will have our I hat in the top column, top row. Then we'll have our j hat and k hat, but first we need to fill in our position vectors going across the middle row and our force vectors going across the bottom row first. So our position vector would be just simply -4, -4 inches. We can drop units for now. Our force in the x component, which would be at first, would be F times cosine of theta, cosine of phi. Now we have these values, so I'm going to go ahead and multiply the force F, which would be 70. Oops. I'm going to go ahead and multiply the force F, which would be 70, times the cosine of the angle 25, and that would give us 63.4 times the unknown cosine of angle phi. Next, we can go and fill in our second column. So we have the j hat, we have 11 inches up, and then our F component, this is a number we have, it's -70 times sine of 25. So -70 pounds times the sine of 25 degrees gives us -29.6 for our force. Next we have the Ki component. We have the position of -d. We'll find this dimension in a minute. And then we have our force vector in the z direction, that z component, which would be 70 cosine of 25. We have this value right here. We already know 63.4 times the sine of phi. So it would be 63.4. We'll multiply it out. 70 times the cosine of 25 again, which we know is 63.4. The difference is for the z component, it is sine of phi, not cosine of phi. So now we have our components in our vector, in our matrix. To find the determinant, we're going to copy down the first two columns. So I hat -4, 63.4 cosine of angle phi, and then j hat 11, -29.6. Okay. Now, to evaluate this determinant, we're going to go down to the right, multiplying, and add these values. We'll then go up to the right for 3 diagonals and subtract these values. So going down to the right, we have 11 times 63.4 sine of phi I hat. So we're going to multiply our answer we just got times 11, and we'll have this is equal to our moment about the origin O is equal to 697.9 times the sine of angle phi. This is an I hat component. Our next product will be 63.4 d times -d cosine of phi in the j hat direction. So we have minus 63.4 times d. And we were adding these, were negative, so it remains negative, times the sine of, I apologize, times the cosine of phi. So you have to be very careful when we're doing our products. Cosine of phi and the j hat. Next, we're going to add these components, -4 times 29.6. So we have -4 times -29.6, which will give us a positive. In the k direction, it will be positive 118.4 k hat. Now we're going to subtract. So now we'll be subtracting our components. So we're going to do subtraction now. So we're going to subtract and put in parentheses up and to the right 11 times 63.4. We know that value. We just got it right here. It is 600. We're subtracting 697.9 in the k hat direction. Next, we'll be subtracting, going up to right here. So subtracting, and in parentheses, negative times negative makes positive 29.6 D in the I hat direction. And finally, we're subtracting, so from parentheses, minus 63.4 times 4, so 63.4 times 4 multiplied 0.4 times 4. So we're subtracting, and this is a negative inside, so it'll be 253.6, and then don't forget the sine of phi. I believe we did forget the cosine of phi right here. We need to go back and add this. 66.9, yes, cosine of phi. And this is subtracting minus a negative, so it becomes positive for both. This is in the j hat direction. So now we can group our components in the I hat and j hat and k hat together. So we have moment about O, the origin is equal to 697.9 sine of phi, I hat here, next I hat is right here. We're subtracting this value, minus 29.6 D, and these are both in the I hat direction. Next we're doing j hat. In j hat we have this positive value, 253.6 sine of phi minus 63.4 D cosine of phi, right here in the j hat. And finally in the k hat, we'll go ahead and move this down to the next line. We have plus 118.4 and then minus our 697.9 cosine of phi in the k hat direction. Next we'll recall we have this moment in the I hat component about the moment of the origin is simply the moment in the x direction, of the x-axis. So about the x-axis, we're told up here, it was given to us in the original problem, is negative 61 pounds of force foot, or foot-pounds. Here we have given moment z, about the z-axis, is given to us as negative 43 foot-pounds for our moment here. Now notice, recall one key insight, our dimensions are in inches. Our dimensions in the problem are in inches. Our moments are given to us in foot-pounds. So we need to convert our moments from foot-pounds into pound inches. So we're going to simply just multiply by 12. So multiply by 12, we have negative 61 times 12. That gives us a moment of negative 732 inch-pounds, or pound inches. And negative 43 times our 12 would give us a moment of negative 516 inch-pounds. So now we can equate these two components of the moment together, the moment about the x and the moment about the z, determine our variable phi and d. Notice this has two unknowns. This equation only has one unknown, so we're going to solve this in the moment about the z first. So I would write negative, bring this in the frame, negative 516 equals 118.4 minus 697.9 cosine of angle phi. We're going to subtract 118.4 on both sides. Alright, so we'd have this would cancel. And then we have our negative 516 minus 118.4, which gives us negative 634. So we have negative 634.4 equals negative 697.9 cosine of angle phi. We then divide both sides by negative 697.9. So we have this value divided by negative 697.9. Oops, had an error in our calculator. Let's see. This number divided by negative 697.9. There we are. So this is equal to cosine of phi. So that means phi equals cosine inverse of this number of 0.90901. Our angle phi, if we do cosine inverse, make sure we're in degrees. Is therefore going to be 24.6 degrees, 63 degrees. So we now found our angle phi. We can use this now to determine our value of d in the moment about the x-axis equation. So set this up. We would have negative 732 is equal to 697.9 sine of phi minus 29.6 times d. We can now substitute this value in, 24.6 degrees. We have negative 732. I'm just going to multiply 697.9 times sine of our answer we just got. So that's equal to 290.9 minus 29.6d. So we're going to subtract 290 from both sides, cancel here. Alright, so we'd have negative 732 divided by negative 290.9, which gives us 2.51 equals negative 29.6 times d. We need to subtract negative 732 minus 290.9. 290. Okay, this is equal to negative 1022.9. We're going to divide now by negative 29.6. We get our distance d is equal to 34.6 inches. So we now solved for angle phi, 24.6 degrees, and distance d, 34.6 inches.
Alright guys, thanks for joining me in another Simple STEM Solution video. Be sure to like and subscribe. Also, if you'd like to support this channel or have particular questions you want answered, be sure to check out my Patreon community via the link in the description below.